Yeah,
Yeah, okay, our next
is
speaker is
that
Elijah Perrier. Will be talking about does the classical quantum distinction matter for AIX? Yeah.
yeah. I
So you got
might
about
just
10 minutes.
do this. Is that okay? Because otherwise you can see two slides at once.
Yeah, this is good. Yeah.
Cool. So, yeah, hi everyone. My name is Elijah Perrier. Some of you may call me from earlier this year. I gave a brief talk on quantum mechanics and AIXI. In this talk today, I'll be looking at sort of giving a very brief high-level overview of some work in progress research I have, which actually came out of that presentation, which is there was a question at the end of that talk around whether the classical slash quantum distinction matters for the uh, description of programs, and in particular how AIXI may weight them. And it's something I've been sort of thinking about sort of on and off. This is work in progress. Um, so yeah, let's get cracking. Obviously, AIXI ranks descriptions. It's universal prize built from programs, so the notion of simplicity depends on what counts as a description. I'll skip through this bit. We all know what Solomon induction is and how it weights programs as per the usual formalism. The kind of basic question I'm kind of interested here is, and it sort of comes out of my earlier talk, and I should have included the diagram, is when uh, when a system like AIXI is functioning only according to classical information processing principles, um, is it appropriately weighting or assigning the appropriate prior probability to quantum environments? We know that classical descriptions of quantum states um, uh, uh, can differ in complexity. And so my sort of question I'm trying to get at with this ongoing research is whether a purely classically constituted AIXI, and I kind of assume people know the difference maybe a little bit between classical physics and quantum physics and classical information and quantum information, but whether classical AIXI is properly weighting, if you like, the likelihood of the probability of quantum programs reflecting quantum systems in the environment. Um, so maybe a little bit of background. Uh, one quote that comes to mind on this sort of topic is in Feynman's lectures. He makes this sort of quip to do with what the shortest description of a physical law might be, and he makes this sort of joke, which is that all of physics compresses into one equation: U equals zero. The content hides in the definition of U here. U reflects the unitary evolution of the uh, universal wave function psi, which is this function here. And Feynman's point is really that this is an extremely terse description of physics, but of course, all the all the detail is in precisely how you specify U. The expression is tiny, but interpretation is not. And this classical description of a quantum evolution, which is what this is here, presupposes that a machine can store, transform, and read quantum states. And so the sort of question then is, are classical descriptions of quantum states or quantum programs sufficient for minimally describing them, or quantum descriptions of quantum states actually a more appropriate way to minimally describe quantum systems? Um, so where my work on this is up to, and again, this is sort of work in progress, and it'd be great to chat with people about this, is the sort of talk here is really about my thought processes. So every short description hides a decoder. So a formula is only short because the machine already knows how to interpret it. And Feynman's provocation was that all of physics can be compressed into a tiny expression because the meaning of the symbols is built into the theory, which is this point before. And so my question is for AIXI theories, does the universal prior assume only classical descriptions, or can quantum states themselves count as programs? And does it make a difference? This is the sort of question that this research project is trying to address. So one way I've been thinking about this, again, this may be, entirely obvious to people who are more versed in some of the literature than I am. I'm a quantum information theorist. That's my background more than AIXI. But the way that I've gone about tackling this program is, well, firstly, we make the hidden interpreter explicit. So we have a description system, and its complexity is sort of given as usual. The complexity can change. Well, what I'm trying to look at with this research is how and whether and to what extent complexity can change when the program, medium, decoder maybe shift from classical to quantum. Um, in a classical case, if two description systems can translate into uh, one another with fixed overhead, then their complexities, as we know, only differ by a small order. Um, the way I'm thinking about this problem is really this sort of classical versus quantum grid, this is
Yeah,
quite
sorry,
common
to let you know that you have like 3 minutes. Yeah, 3 minutes. Yeah.
okay. All right, 3 minutes. Yeah, so basically there's this question. We have classical descriptions and quantum descriptions. We have classical decoders that take those descriptions and quantum decoders. And so the question is, um, what are the differences that would arise in this case? There is literature on this topic. There have been several proposals for quantum Kolmogorov complexity. They effectively differ as to whether the description is classical that then feeds into a quantum decoder or a quantum computer, or whether the actual description itself is quantum. And what I'm curious about is what are the implications of AIXI for these different forms of quantum Kolmogorov complexity. Um, so the sort of main point maybe to take away is that a quantum state may be um, uh, uh, cheap to supply directly, but it may be expensive to generate from a classical description. And so we sort of see this here on the so so I may be able to describe a quantum state using another quantum state with n qubits and put it into a quantum decoder slash quantum computer to build my quantum state. Whereas if I had to do that classically, I effectively have an exponential overhead to properly describe the same quantum state. This is the basic distinction between classical and quantum. And so the kind of question I'm looking at with this research is how would that then impact AIXI when it's trying to weight uh, each of these states? Should it be using a quantum description of a quantum system, or is a classical description of a quantum system going to give it, if you like, a skewed probability or not? I probably don't have much time, sorry, to go through the rest. I thought I had a little bit more time. Um, where I'm at is I believe that there is a separation here between quantum and classical, which is pertinent to AIXI. The kind of fundamental point is that I think that there is a justified claim that when AIXI is seeking to weight quantum programs, that actually to appropriately weight them, it ought to avail itself of a quantum description, which fundamentally means encoding that description in a quantum state, which means basically having access to a quantum computer of some sort. I'll leave it there because clearly I don't have much more time, but that's the work I'm working on now. If anyone's interested, please reach